Hello, in this video I'll be talking about section 5.1 on polynomial functions. So just some vocabulary. When I say monomial, you might know mono means one. Monomial is sort of a building block of a larger function. And it can be a real number or a variable or a product of a real number and one or more variables with whole exponents. So examples of monomials could be the number 3, the variable x, something like 4x squared, something like negative 1/2 x to the 7th. This number can be somewhat unusual, but as long as the power of x is a whole number, that's an example of a monomial. And the degree of a monomial is just the power of the variable. So degree 7, degree 2, degree 1, because that's x to the first. And if there's no variable at all, we'd call that degree 0. If we add or subtract a bunch of monomials, we call that a polynomial for many. And the degree of a polynomial is the largest degree we see after simplification. And if something has a formula that's a polynomial, we call it a polynomial function. So just as some simple examples, I might have something like f of x is 3x to the 8th minus 11/2 x to the 5th plus 2x squared plus 13. This is a polynomial. 4 terms, that's what we call what we add or subtract, each one of which is a monomial. Degree 0, degree 2, degree 5, degree 8. We would say that the whole function has degree 8. That's the biggest degree we see. I could have a different polynomial function, negative 1/2 x to the 5th plus 11x to the 4th plus x. 3 monomials added together give us a polynomial. Degree 1, degree 4, degree 5. We would say that overall, this polynomial has degree 5. And by standard form, what I mean is I've written all of the monomials separately, and they're in decreasing order by degree. Biggest power is 8, so I write that first. Next biggest power is 5, then 2, then 0. Now, not every polynomial has to be written in standard form. I could have something like h of x equals x cubed minus x to the 8th plus 4x cubed plus 2x to the 5th. So there are some like terms that could be grouped together. We could switch the order around. But just looking at this, we know that it could be put into standard form. Or maybe I have something that's been factored. 2x squared minus 1 times 3x to the 5th plus x. If I wanted to, I could FOIL this out and rearrange the terms. But I don't need to do that to understand that it would be a polynomial when I finish with that. So just as a warning, graphs of polynomials can get pretty complicated. It's going to be nearly impossible for us to look at a polynomial function and know everything about its graph. But there are some things we want to identify right off the bat when we look at the graph of a polynomial. So get in the habit of kind of reading the graph from left to right. Yes, it's going to go up and down, but try to follow it from left to right. And ask yourself, where is the graph increasing? Where is it decreasing? Where are the turning points where it makes a transition between increase and decrease? And then, what's going on the extreme left and the extreme right? The graph of a polynomial will always go really, really, really high or really, really, really low if you go far enough to the sides. So notice that pattern. So let's look at a couple of examples. I will graph f of x equals negative 2x to the 3rd plus x squared plus 7x plus 1. And I have this already set up on Desmos. Here's what our graph looks like. So I'm going to try to read this from left to right. Right around here is the leftmost part of the graph that I see. As I move to the right, we're going down. So right now we would say that the graph is decreasing. As I move to the right, it's also going down. Then right around here we have what's called a turning point, and it's increasing. I'm continuing to move left to right, but now I'm going up as that happens. I have another turning point, and then it's decreasing again. So the rough graph here, it looked something like so. So moving left to right, it's decreasing, then increasing, then decreasing. That kind of is a rough description of the behavior. There's a turning point here and a turning point here. And the end behavior is what's happening at the ends. There's some wiggle in the middle. But if we zoom out on this thing, on the left, we have values that are way up at the top, so it's positive on the left. On the right, we're way at the bottom, negative on the right. We call that the end behavior. There's some middle behavior, but the end behavior is positive on one side, negative on the other. I have another example here. X to the 6th minus x to the 4th minus 2x squared minus x. That looks something like so. Kind of a lopsided W. As I follow this one, decreasing, turning point, then increasing, turning point, then decreasing, turning point, then increasing. Graph was something like that. Decreasing, then increasing, then decreasing, then increasing. That's the overall pattern that's worth understanding. 3 turning points along the way. In the end behavior, it's positive on the left and positive on the right. So even without a lot of detail, it's a way of understanding the rough pattern of the graph. Sometimes graphs go up, sometimes they go down. For a polynomial function, you want to pay attention to that pattern of how it's going up or down or changing. And it turns out that the end behavior can be predicted by the leading term. So the leading term would be the one you write first in standard form. So there are really 2 questions you want to ask yourself. You want to look at that leading coefficient A and ask yourself, is it positive or negative? And you want to look at the degree n and ask yourself, is it even or odd? So I'm going to make a little table here. And once we know those 2 things, we will know the end behavior for that polynomial. Even degree is like degree 2, like a parabola. So if we have an even degree and a positive leading coefficient, the end behavior will be like an upward opening parabola. There might be some wiggle in the middle, but it will be positive if we go far enough to the left and positive if we go far enough to the right. If we have a negative coefficient in the front, it's upside down. So negative on both sides, maybe some wiggle in the middle. If we have an odd degree, the sides don't agree. If we have an odd degree with a positive leading coefficient, it'll be positive on the right and negative on the left, again, maybe with some wiggle in the middle. If there's a negative in front, it's the opposite. Now, I'm not saying you have to have all this memorized, but you should have access to this information so you can quickly use it. Polynomial graphs are very complicated, but it is nice if you can just kind of look at a polynomial and know at the very least what its end behavior will be. So as an example, I'll just make something up kind of randomly. H of x is negative 2x to the fourth plus 7x to the third plus x squared minus 11. Here's my leading term. I notice that the leading coefficient is negative, but the degree is even. That puts me in this category here. So my end behavior will be negative on the left and negative on the right. Maybe there's some wiggle in between, but that's what we're expecting to see. So I'm going to go back to Desmos and graph this. We'll see if that's the end behavior we get. So we had y equals negative 2x to the fourth plus 7x to the third plus x squared minus 11. So there's a little bit of a wiggle here. We'll notice here it has kind of this unusual behavior. But as I zoom out, what I notice is on the left, I have values that are way down at the bottom, and on the right, after I go through my wiggle, I'm also way down on the bottom. And that only depends on starting with negative 2x to the fourth. I could make changes. I could put in 17 here. I could put a negative 8x squared. That changes some of the details of the graph. I could put a plus 5x here. Right, I've changed some details of the graph. I've put a little wiggle in it. But eventually, if I zoom out on this, right, so there's a peak way up here that's kind of hard to see. But if I change my window, I'll be able to see that, yeah, there's some wiggle to this, but on the left and on the right, we're down at the bottom. Down at the bottom here, down at the bottom here. And that's what we predicted. Unless you know a lot of calculus, it's going to be hard to know all the details of a graph. So really pay attention to what we do know. We do know, roughly speaking, what it's going to do on the left and right. And if you want to know where the turning points are, your calculator can find them. So I'm not going to go through all of this. We did it in class. But for a function like this, the graph looks something like so. There are two turning points. One of the turning points is what's called a local maximum. A local maximum means it's taller than everything nearby. So for example, if I were just to look at what's going on in that rectangle, the turning point is the highest point in that zone. Similarly, the turning point here is called a local minimum. If I'm only looking in that zone, it's the lowest point. It's not the lowest point on the entire graph, but locally it's the lowest point. And if you use the Analyze menu from your graph, you can select maximum or minimum to find those. So we did this in class. What we wound up finding is that this turning point occurred when x is negative 0.366 and y is 2.598. The other turning point occurs when x was 1.366 and y was negative 2.598. And the symmetry there is not a coincidence. It does have to do with nice features of this function. So if I know where those turning points are, I can describe the x values where the function is increasing or decreasing. We always describe increase and decrease in terms of x values. So what we can kind of do is we can imagine we're comparing this to a number line, and here is where x is negative 0.366 on the number line. Here is where x is 1.366. And what I'm noticing is if I read this graph from left to right, before I get to the first turning point, I'm increasing. So we have this zone where we're increasing. Then I have this relatively short zone between the turning points where I'm decreasing. And then after that second turning point, again, reading left to right, I'm increasing again. This graph goes up, then down, then up. So it's increasing, then decreasing, then increasing again. And we want to describe those zones of increase and decrease in terms of the x-coordinates. So our first zone of increase is before we get to this x-coordinate. So thinking in terms of the number line, if we're to the left of this, we could say x is less than negative 0.366. But we're also increasing after the second turning point. So we're to the right of this number on the number line. X is greater than 1.366. We're describing which x values, and we're using inequalities to do that. Before means you're less than something on the number line. After means you're greater than something on the number line. We're decreasing between those two values. And between can be expressed with a compound inequality, like so. X is between these two values. It's greater than this one and smaller than that one. So this takes a little bit of getting used to describing portions of the graph just by paying attention to the x-coordinates. You really have to focus on the left versus right, even though you see the up versus down. My first zone basically occurs to the left of the first turning point. Then I have a zone between the turning points. Then I have a zone to the right of the second turning point. X is less than the first turning point value. X is between them. X is greater than the second. So that is it for now, and I will end the